So in this video, we're going to take through OCR Module 5, looking at circular motion and SHM. So some useful things while you're using this video, I've put a link in the description to the notes template you can see on the right. So the best way to use this video would be to download a copy of that template and then work your way through and fill in as much as you can in each section, and then watch the video in that section to review and improve your knowledge of that section. And this isn't a task you should complete once. This is something you should be aiming to do repeatedly in preparation for the exams to make sure your subject knowledge keeps developing. Okay, so a resource I've created to help you with this is on a website called Memorize. Again, I've put a link in the description to this course. It will help you practice your definitions so you can recall them with no effort whatsoever. Okay, so let's get started looking at 5.2.1, looking at circular motion. So what I like to do is work your way through this section on the template, and then we'll review it. Okay, so I'm going to assume you've done as much as you can for the template. So let's take a look. So a radian is the angle you get at the center of a circle when the arc length is equal to the radius. That's how it's defined. So when we're doing circular motion, we pretty much exclusively work with angles in radians, and then all the other things come from that. So we're going to look at some other things we use to describe the motion in a circle. So one of them is the time period, which is the time taken for an object to complete one full circular orbit. And then we have the frequency, is the number of circular orbits completed per second. Okay, so we're going to think about experiments you might do to test out circular motion and some strategies you're going to use to try and make those measurements as accurate as possible. And the thing we usually measure is the time period. And now I think there are 5 things you can do to try and improve the accuracy. So the first thing is you set it going in a circle and you let it settle into the motion by allowing it to do a few circles before you start timing. Then what you do is, instead of trying to time one circle, you time 10 full circles and divide that time by 10. I wouldn't just do that once. I would repeat that process twice more. So I've done 3 sets, and then you calculate an average, and that helps you reduce any random error that might affect your results. I'd use a fiducial marker to mark the start and end points of the circular orbit. It makes it easier to time it accurately. And finally, what I would do is I wouldn't be trying to time it in real time. I'd video it and use a slow motion camera, so it makes it really easy to pinpoint exactly when it's the start and the end of a circular orbit. Okay, so next we're going to define another property we use to describe objects in circular motion called angular velocity. And it's the number of radians swept by the radius of an object in circular motion per second. So imagine a radius drawn from the center of the circle to where the object is, and then when the object's moved around the circle, that radius will have moved to a new location, and it's the angle between those two radii. And we can calculate angular speed using the time period or the frequency using these equations we can see here. Okay, so next we're going to think about how we can cause something to be traveling in a circle. So again, what I'd like you to do is work your way through this section, and then we'll review it. Okay, so first of all, let's describe what we mean by uniform circular motion. So it's when an object travels at a constant speed and there's a resultant force always acting towards the center of the circle. So the resultant force essentially can't act in any other direction apart from towards the center to be in uniform circular motion. And we don't just use angular velocity to describe objects, we can also calculate their tangential velocity in meters per second, and we can do that by working out the total circumference and divided by the time period, which then we can see happens to be equal to the angular speed times the radius. So now what we're going to do is describe something called centripetal acceleration and see how we can calculate it. So you get centripetal acceleration when the acceleration is always directed towards the center of the circular orbit, which means the resultant force also has to be directed towards the center. That's what Newton's second law tells you. They have to be in the same direction. And we can calculate it using this equation. So we need to know either the tangential velocity or the angular velocity and the radius. Okay, so once we know the acceleration, we can calculate the centripetal force, and we're going to assume the mass of the object is constant, so we can use F equals ma, and we end up with these equations here. And then what we can do is we can actually do some experiments to test this out, and the way you usually do this is by whirling a bung around your head. So that's essentially what you're going to do. You're going to create circular motion with a mass on a string, and you're going to essentially investigate the relationship between radius and the time period. So you're going to pick a radius by measuring out length of string, and we're going to attach a mass to the end that we're going to keep constant throughout. And we're going to put another mass on the other end of the string that's going to be creating a centripetal tension force. So again, that's going to be fixed as well. And then what we're going to do is we're going to make the object go round our head in a circular path. So again, thinking about what we talked about earlier, we'd let it settle into its orbit, measure time 10 oscillations using a fiducial marker, and repeat this for each length. And then what we will do is we will change the length to 6 more radii and measure the time period at each radius. And what we should find is that if we plot a graph of t squared against r, it should be a straight line passing through the origin because the mass and the tension force are constant, which means we should get t squared as directly proportional to r using the equations. Okay, so that's, if you want to see the algebra version of that, what we do is we make a substitution for the angular speed for 2 pi over t, and then we can rearrange it to see that t squared is directly proportional to r if m and f are constants. Okay, so moving on to simple harmonic motion. This isn't really a change of topic because circular motion is also simple harmonic motion, but they're usually described as different topics. So these are the things that the specification says you need to be able to do. So let's take a look through these. So let's start off by defining some properties. So again, work your way through the section, then we'll take a review. Okay, so displacement of an object in SHM is how far the object is from its equilibrium position, and it'll be measured in meters, but you can also get angular displacement for a pendulum or an object in circular motion measured in radians as well. Amplitude would be the maximum displacement from the equilibrium position, and again you can have angular amplitude as well. Time period is the time it takes to complete one full oscillation, regardless of what kind of oscillation it is. Frequency is the number of oscillations per second. Then moving on, angular frequency is the number of radians per second traveled by the object, and we get that by representing the motion using sine and cosine functions. And then if we want to start thinking about the phase difference between points in a cycle, so if we've got 2 points on a wave function or 2 points in an oscillation, we can express the difference between those as an angle, or we could express it as a distance, or a velocity or whatever you like. So if we want to calculate angular frequency, we do it using these equations here. Okay, so let's now define what we mean by simple harmonic motion so we can start to think about modeling it. So it's when the magnitude of the acceleration is directly proportional to displacement, but the acceleration is in the opposite direction to displacement. So anything that fits this criteria is said to be in simple harmonic motion. Okay, so the thing we're going to end up doing quite a lot in this topic is actually taking measurements of an object in simple harmonic motion. And just like before, we often measure the time period, and you'll notice the strategies to improve your accuracy are pretty much the same. So we allow it to settle, we time 10 oscillations, we do repeat readings and get an average. The only difference really is where we place the fiducial marker. So for circular motion, it was at the we placed it at the start of an end of the circular motion. Here we place it at the equilibrium position, because that's the point it's guaranteed to travel past in its motion. But everything else is pretty much the same. So what we're going to do now is, when we're modeling SHM, we can express its displacement using sine or cosine functions, depending on where we start from. So let's actually see why that's the case. So the general condition of SHM is the acceleration is directly proportional to displacement, but in the opposite directions. And the constant of proportionality turns out to be the angular frequency squared. So we get that equation there. But we could also express acceleration as the second derivative of displacement, or you've taken the derivative twice. So there are only two functions where the second derivative is minus a constant times the original function, and those two are the sine and cosine functions, and I've shown you there what you get if you do the second derivative of each. We end up with exactly the same thing. If you'd like to see more conclusive proof of this, you will need to have knowledge of exponentials and complex numbers, but do have a look at that on the internet, because it's quite interesting to see that actually proved that there are only two functions, these two. So next we'll look at another equation we often use to model SHM. We can calculate the velocity at a given displacement. So we start with exactly the same equation, but we approach it in a different way. Instead of putting acceleration as the second derivative of displacement, we can also make it equal to velocity times the derivative of velocity with respect to displacement. And then what we can do is we take dx to the other side, and we get rid of those partials by doing integration. So we're going to start from where the velocity is 0, so where it's which means it's initial displacement with the amplitude, and we're going to find out where its velocity v is at displacement x, which is where that equation comes from. Then what we can do is we can essentially plug our values in, rearrange to make v the subject, and we end up with that equation we have there. So then next thing we're going to look at is, you should know that for SHM, the time period is independent of amplitude. So we want to know at which conditions that is true. So first of all, we should know the equation for displacement is a cosine omega t, or we could have done sine. And after one time period, its displacement should be back where it is, which means omega t is equal to 2 pi. So after one time period, that means the time is going to be equal to 2 pi over omega. So the section in brackets becomes 2 pi. And you see none of those properties in there require amplitude to calculate it. So you can see the time period is essentially independent of amplitude. So there are some provisos for this. So with a pendulum, a pendulum can only be modelled as being an SHM for small angles, when sine theta is approximately theta. And that's only true when the angular amplitude is less than 10 degrees. And for a mass spring system, it only obeys the laws of SHM when it's obeying Hooke's law. So again, we need to keep the displacement below the elastic limit part of it. Okay, so what we're going to do is we're going to have a look at how we can construct graphs of objects in SHM, so the displacement, velocity, and acceleration graphs, or the motion graphs. So if we have a displacement equation, displacement is 4 sine 2t. What we can do is get expressions for the velocity and acceleration using differentiation. So if we take the first derivative, that's going to be velocity, and the second derivative is going to be acceleration, and that's what allows us to sketch the graphs you can see on the right hand side. So the blue one is our displacement. We can see the acceleration is the grey one. We can see is the exact opposite, so it's directly proportional but opposite direction, whereas the velocity is 90 degrees out of phase because it's a minus cosine function. Okay, so now we're going to start thinking about SHM in terms of energy as well. So we're going to look at first at a pendulum at the energy changes, starting from maximum displacement. So at maximum displacement, you have maximum potential energy, which for a pendulum is GP. And as it goes through the equilibrium position, you'll have maximum kinetic energy from the transfer of GP. And then when it gets to the opposite side of its cycle, it's got back to GP again. But we're only halfway through a cycle at this stage, so it repeats. It has maximum kinetic energy at the equilibrium position and then finishes back with GP. So we can do the same thing for a mass spring system, but this time we'll start where it has maximum velocity. So it starts off with maximum kinetic energy, which gets transferred to elastic potential energy at maximum displacement. It transferred back to kinetic energy as the mass comes back to the equilibrium position. It then does the exact same thing on the other side, transfers to EP, and then comes back to kinetic energy again at the equilibrium position, and it's now completed one full cycle. Okay, so we're going to have a look at sketching the graphs for the energies of, so we're going to look how we've attained the graph we've got here. And we're going to start the graph from where it has maximum velocity, which means its initial displacement is 0. So that means we're going to use a sine function for its displacement. And that means we're going to start at 0. Even though we're squaring the sine function, 0 squared gives you 0. So that's why we're going to start at 0 for the potential energy. Kinetic energy is maximum at the start, so that's going to be given by our cosine function. And we've got a cosine squared graph. But if it's undamped, the total mechanical energy stays fixed the whole time. So the sum of kinetic and potential energy should be equal to 0 the whole time for this graph. All right, so now we're going to move on to look at applying external forces to a system, looking at applying forces to decrease the energy of the system and also to increase it as well. So we're going to start off by damping, so decreasing the energy. First thing, we're going to describe some different scenarios. So when we describe something as being in free vibration, what we mean is there are no external forces acting, so mechanical energy is constant. When it's damped, we say it's experiencing an external force to decrease the mechanical energy. And when we're in forced vibration, we are applying a periodic external force to it. So they're all slightly different scenarios. So damping is a specific case where we're decreasing the mechanical energy of the system, which means it acts in the opposite direction to the velocity of the object. And the effect it has is it decreases the maximum amplitude and it decreases the maximum velocity as well. Okay, so now looking at forced vibration, resonance is a specific case when the periodic external force has a frequency equal to the system's natural frequency. And what we mean by a natural frequency is the frequency at which a system would oscillate if it's given an initial displacement and then allowed to freely oscillate. And we can see the effect of this. So as we change the frequency at which we force a system to oscillate, we get different amplitudes, but it ends up being maximum at the natural frequency. And if it's undamped, there is infinite amplitude at resonance, but as we apply damping forces, we bring the amplitude down, as you can see in the graph. So now what we're going to do is we're going to look at an example of forced oscillation and resonance, and a really nice example is a Barton's pendulum, which looks something like this. So we've got a large mass that is providing the periodic driving force labeled P, and we've got it connected to a series of other pendula of varying lengths. So first of all, let's talk about pendulum Y, which has the same length as pendulum P, which means it has the same natural frequency as P. So what's going to happen is Y is going to be in resonance and have a much larger amplitude. And what you'll also notice is its displacement is 90 degrees out of phase with the driving pendulum displacement. For pendulum X with a shorter length, it has a higher natural frequency than P. So P is going to force it to oscillate below its natural frequency. It'll have a fairly small amplitude and its displacement should be in phase with pendulum P. If we then look at Z, which has a longer length than P, which means it has a smaller natural frequency than P, so P is going to make it oscillate above its natural frequency. So it will have a small amplitude and its displacement will be an anti-phase with pendulum P. Okay, so that concludes this video looking through the circular motion and SHM part of the specification.